Well, welcome back to the class, to the session. Well, last time we had discussed about the normal distribution. We have seen the examples, right? And we have seen the way how to read the tables, right, importantly. And also, we had seen the central limit theorem, which is the theorem that, we have a simple random sample that the sample mean can be approximated, or not approximated, can be approached, right, to normal distribution actually. And the sample mean, the mean of the sample mean, right, is actually distributed as normal distribution with the mean and the standard deviation shown like before, right? The mean will be the same as the population mean, and the standard deviation is the population standard deviation divided by the square root of the sample size. Basically, the hardest part is to make sure that the sample we get is the simple random sample. Right? That I think is the hardest part to be sure, but that is not what we worry about in our course. What we worry about is, well, if the original population is normally distributed, right, that's first condition, or it could be, if we don't know the distribution, if the sample size is big enough, right? It's big enough means in our book defined as bigger than 30, right? If it's big enough, even though the population is not normal, we can all still approximate the sample mean as the normal distribution, right? That is the central limit theorem states. Right? And last time we have mentioned, right, the binomial distribution, like what we had before in the previous chapter, right? If we find the probability of that, even single one may be not that hard, but it's still tricky, right, to find the probability of it. And luckily we have table to do that. Someone, or our book has done that for us, like for the multiples of tenths probability of success, and also for the number of trial is smaller and no bigger than 20, I think, right? But if it's more than 20 of the sample size, or if the probability of success is not that multiples of 10, right? It will be very hard to do. If in the case we want to find the probability of at least something success, certain number of success, or at most or less than or greater than a certain number of success from some number of trials, it will be relatively harder. Like for something, it could be given x follows binomial distribution of 500, even 0.5, right? Like flip the fair coin 500 times and ask what is the probability we can get the number of heads to be at least 300. X is the event that number of head from flip a fair coin 500 times, right? that even though the coin is fair, right? So it is still very hard to find the probability to get number of heads to be at least 300, right? But as we mentioned last time, right, the nature of binomial distribution could be approximated to normal distribution if, in some case, of course, the number of success and the is not that effect, and the trial is a lot, which means the NP and NQ n times 1 minus p is a little less large. So normal so such way we can approximate the binomial to normal distribution. That's why it's in this chapter, right? And if we have it approximated, then we could convert the individual probability, like the question we had before. I just erased from 300 to 500, that 201 different probabilities, into a normal distribution, which is a little, could be a lot easier. The random variable x follows a binomial distribution with two parameters of number of trials and probability of success, n and p, correspondingly. So the condition is if n times p is big enough, and n times 1 minus p is also big enough. Big enough here means the product are at least 5 for both of them. We need to check the condition for both of them, and p and n minus p. Right, then x can be approximated by a normal distribution. Well, what we know is the normal distribution need to have a mean, need to have a variance as the parameter, which binomial distribution also have the mean and the variance. Right, so where this mean of the approximated normal distribution is n times p, and the variance is np1 minus p. Which are the mean and the variance of the original binomial distribution, but in this case they are normal distribution. Right? In other words, x is the random variable now, is the normal distribution, with such mean and variance. Of course, another thing need to be considered is this binomial distribution was a discrete distribution, and normal distribution is a continuous distribution. We approximate the discrete distribution to or by a continuous distribution. Something we need to do is called continuity correction. Right, so we'll see the continuity correction later, continuity correction is needed for the type of approximation. So let's see the basic idea when we see the example. Right? Let's see the examples. But before we see example, right, a couple of things need to be highlighted again. Right, the original was binomial with parameter n and p. It can be approximated to the normal distribution with the mean of np and the variance of np1 minus p as the mean and the variance of the binomial distribution. And the only thing, or the extra thing we need to do is, before that, we need to check the condition that n times p is at least 5 and n times 1 minus p is also at least 5. Is at least 5. And also, right, after we consider if it could be approximated by normal, then what we do is to do the continuity correction. Once again, also it is just the approximation, so only do that type of approximation if question is asked us to do the approximation. Right? If it's not asked, then we just should use the original binomial probability distribution to find the answers instead of the approximation. Only do that when asked. Right, so this probability looks like, well, it has to be done, or it's better need to be done by the binomial approximated by normal distribution. Right, since, well, we find we have 200 passengers and at least 120 are being are boarding for the man, then it's need to unload cargo. Right? That is the case, which means the plane is too heavy, right? So it has to unload the cargo to make sure it flies more safely. And so also assume that men and women are equally likely to show, which means what we have here is the 200 passengers, and equally likely to show means the probability of a man shown is also equals to the probability of women to show, is both of them are 0.5. Right, so the number of men in this case is the random variable. Right, the number of men appeared or boarding on the plane, right? And the probability the plane needs to unload cargo is the probability that the man boarding is at least 120 from 200. Right? So the body of the question tells us the number of men appear follows a binomial distribution, that 200 is total people will appear, and the 0.5 will be the likelihood of a man appear. Right, that's 200 and equally likely for a man and women appear. And what we are asked is to ask us to find the probability of x to be greater than or equal to 120. Right, so if we use the usual binomial probability, we'll do from 120 to 121 all the way to 200. That will be 81 different formulas to do, right? Which maybe it takes about maybe 4 or 5 hours to do, right? If you have Excel, that will be much shorter, but we do not use the technique of Excel, so we can see the approximation there, right? That's another way. But of course, if we have Excel, that will be a little easier. So in this section, in this topic, we just see that, well, normal approximation can help us if we do not have any other techniques. So we need to check conditions. This one is tough to do, so we check the conditions. Of n times p and n times 1 minus p. 200 times 0.5. The first condition is satisfied. Second condition is n times 1 minus p, which the probability of success is 0.5. The probability of failure is simply just 1 minus 0.5 is also 0.5. Also satisfy the condition. Therefore, our x, or random variable number of men, can be approximated by the normal distribution. which the mean is the n times p. We just check that in the condition is 100. The variance is n times p times 1 minus p. That's 200 times 0.5 times another 0.5. Is 50. Right, so that the x can be now approximated by normal distribution of 100 is mean and the variance is 50. Right, so the x could be approximated by normal distribution, but as we mentioned, right, the binomial was discrete, normal was continuous. So when we approximate the binomial by normal distribution, something called continuity correction is need to be done. That it is at least 120. So, like the histogram we have seen before, right? For the individual cutting value or some intervals has gap in the middle, what we could do is we use the midpoint of each gap to extend the interval and make the intervals connect together. Right, so the midpoint of each individual value, like we have here for 120, well, it could be 119.5 or 120.5 as the selection. And since we have one greater than or equal, right? So the continuous interval selected need to cover the point of 120. So we have selection of bigger than 119.5 or bigger than 120.5 as the continuous case. But we will choose the one cover the 120 as the point because we have the equal sign. So we use 119.5 as the value of the continuous random variable. Right, we will see some rule later on, but the main idea is if we have the equal sign, we choose the interval cover it. If we don't have the equal sign, we choose the interval that don't cover it. It's from the discrete number to continuous number, it is differ by 0.5 on the left or on the right to check. And in this case, since we have the equal sign, we go greater that we need to use 119.5 to cover the number. And we convert the z-score, that 119.5 minus the mean of 100 and divided by the square root of 50. We'll get the value of 2.76, right? You can try it. I could erase this part. So we could try it, right? The z-score is x minus mean over the standard deviation. That's 119.5 minus 100 of the mean divided by the square root of the variance. Right, then we can go to the standard normal distribution. And go to the table, right? The first two digits are 2.7, the third digit is 6. Then we get the table value and subtract by 1. which we have seen the way how we do that, and the answer will be 0.0029. We'll continue the correction from the binomial to normal distribution. That's in total 5 cases. Right, the first one asking for probability x equals a. And then for the normal distribution, since it's asking for the point, right? So the interval we're taking will be the a minus 0.5 to a plus 0.5. The left will be one differ, and the next one, but for the number a, if asking for just this one, then to do the continuity correction, we just find the interval of the probability from a minus 0.5 to a plus 0.5 of the x value. For a and bigger, that was the case we had seen in the last example, right? A that have two choices, a minus 0.5, also a plus 0.5. For a and the bigger, that's the right one, and include the point A. Right, so our interval we choose should include the point A as well. So for the continuous version, we're asking for probability of A bigger than or equal A minus 0.5. Actually, for the continuous probability, right, with or without equal sign is actually same, right? We do not have a mess for the single one line under the curve, right? For a single point, but not interval, we cannot have probability. So either with or without the equal sign actually does not affect the answer at all. Right, similarly, when we're asking for bigger than a, which doesn't include the a, right? With bigger than a means from a plus 1 to a plus 2 all the way to n. That doesn't include the a, so we need to choose the interval does not include a. Right, this a plus 0.5 and bigger for the continuous version doesn't include a inside. Right, so when probability of asking for x bigger than a for the binomial distribution, then when we do the normal approximation, we will find is a plus 0.5. Right, and for the smaller, if we have less than equal, that is a or b or left, you can take a guess, right? The a or less means includes the a, So we have two choices. If we go to the left from the point to set an interval, the way we cover A inside is to make it a little right. In that case, it can include A, right? So we're getting for the probability x less than or equal to A plus 0.5. And the last one for asking for A less than A, which is from 0 all the way to A minus 1, right, in the discrete version. And in the continuous version, we have still 2 points to choose. From that point to the left will not include the value of A, which is the A minus 0.5. So that is the usual 5 different cases for the binomial distribution, and if a random variable could be approximated by the normal distribution, then that is the continuity correction we need to do. Right? For a different number, the equal sign actually doesn't matter for the continuous case, and whether we plus or minus 0.5 is important and is decided this way. So that's the cases we can follow. All right, and next question. Assuming getting a newborn boy and a girl are equally likely, right? So to estimate the probability of getting more than 36 girls in 64 births, use normal as an approach if possible. And this one certainly is a binomial distribution, right? That's 64 new births, equally likely for a boy and girls, right? And asking for getting more than 36 girls. Getting more than 36 girls is the probability asking. And what we know that is this one follows actually a binomial distribution. And asking for probability more than 36. Right, so we know that it is a binomial for sure. Right, the condition of binomial you can check, right? It actually follows that. And asking for probability more than 36 of them, that if we actually finding probability by the formula, right, that we need to do what? 28 different probabilities use table, which is doable, but it's kind of longer. Right, and they say, well, just getting a approximation idea, and we can use the normal approximation if possible. Right? So we check the conditions. Right, conditions say np and n times 1 minus p need to be at least 5, that we get np is 32, and n times 1 minus p, of course, will also be 32. It's not always equal, it's 0.5 and 1 minus 0.5, right? Maybe right now it will be a little better. Right, we get n times 1 minus p is also at least 5. Actually, it's bigger than 5. Right, so which means the x could be approximated by the normal distribution. Where the mean of the normal distribution is np, which was found 32, and the variance np times 1 minus p is 64 times 0.5 times 1 minus 0.5, which is 16. Oh, which is 16. So probability for x bigger than 36, as we know, we need to do the continuity correction. Continuity correction is only for the normal approximate to the XA binomial distribution. Right? Normal approximate to the binomial. That's the only case we use. Maybe some other case in some other book are using it, but for our book and for our course here, we just use this one. Right, so when we continue the correction, if you have wrote down, right, what it's supposed to be, that we need to take is 36.5. Right, then we calculate the z-score, 36.5 minus 32, divided by square root of 16. Even though 1.125 may be the answer, right, but we're still rounded to 1.13. So that is probability of x, the z-score, right, not x no more, convert to standard normal distribution. Right, these two x. This x is followed by binomial distribution. This x is now, if after we do the continuity correction, is follow or approximated by the normal distribution. 1.13 that is 1 minus 3 of 1.13. And we go to the table to take out the phi, which is 0.8708. And finally we get 0.1292. Right, so that is everything of the chapter 6 called normal distribution. Alright, so we'll move on to chapter 7.